Oh, hey, it's your friend's dog with the snaggletooth, Alie Ward. We're going to take a deep breath, all right? We got this. We got it. And let's get illuminated on the topic of black holes, shall we? So, this ologist is a theoretical astrophysicist and a cosmic origins scientist in the Astrophysics Science Division at NASA's Goddard Space Flight Center in Maryland. And he got his bachelor's in physics, a master's in condensed matter physics, and that deals with how matter arises. And then he just topped off those degrees with a casual PhD in theoretical astrophysics at North Carolina Agricultural and Technical State University. So we were introduced by Ologies' fan favorite guest. You love her, Dr. Raven, the science maven Baxter, and I trust her taste in everything. So I asked this NASA scientist to please meet me the next time he was in LA and be prepared to steel himself for questions that a 6-year-old might ask about what is a black hole. He obliged and explained things so well, we're all going to learn enough to impress at least an 8-year-old, but also maybe the people who work in our office who are going to think that we're geniuses. So he showed up. He was wearing the coolest boots I've ever seen. They were this like dressy above the ankle with like embroidered gold floral motifs, and we headed into my home studio with 2 cups of tea and a small goblin named my dog. But okay, so the ology for this one is black hole theory cosmology, and it's a lot of words, but it's heavy stuff because a black hole, it's a spot in the universe where gravity and space and time go hog wild. Things go bonkers, and it's so strong, nothing can wrestle from it, not even light or you. So where are they? What are they? What's at the center of them? I don't know, but this guest does and is going to fill us in. So get ready for a dazzling two-parter that starts with the 101 of black holes, absolute basics, busting of flim-flam, the major players in the history of theories, what happens when they collide, how do we image them, what's the most giant, dense book you can buy about them, where do trad goths fit into this episode, does my dog exist, how many of me are they, the hows and how many's of black holes, how astrophysics is like drawing, and the greatest gift that he could give his mom with theoretical astrophysicist and black hole theory cosmologist, Dr. Ronald Gamble.
Ron Gamble, he, him, his.
All right, let's get into it.
My work is entirely focused on the theory of black holes. So a lot of people work on just observing them and they're really looking at the matter around a black hole. I'm like, no, what is a black hole? How can we move our, how can we get to one, maybe? What's the theory around it? What's the math? Can I make new math to study a black hole? Do I need new math? Do I need to break my brain to study this?
Mm-hmm.
Of course, you mentioned cosmology,
Mm-hmm.
and that's a more kind of larger scale, kind of like an esoterical almost. What's our place in the universe? Where did the universe come from? How many black holes are there? Was there a black hole at the beginning of the universe?
Mm-hmm.
Is there going to be a black hole at the end of the universe? Who knows? But nobody panic, because that's a very long, long way away.
Like, what about, is there one in the middle of most solar systems? Let's pull
Mhm.
back. Where exactly are we and what's in the center of the galaxy? Our galaxy.
So if you look at the map of a Milky Way, right? The Milky
Mm-hmm.
Way is a spiral galaxy. If you look at the arms of the spiral galaxy and you go kind of 2/3, a little, maybe a third out,
Mm-hmm.
that's where we are. That's where the solar system is.
Okay.
So we're in like a very sweet spot in the galaxy. Earth is in a sweet spot in the solar system. We are like perfectly placed.
And just in case you're blanking, as far as we know, there's one universe. In that universe are up to 2 trillion galaxies. And the Milky Way is just one of those 2 trillion. And in the Milky Way, there are about 100 billion stars, including our one little sun around which your planet revolves. So we're up here, we're worried about things like nose hairs and how many likes our baby announcement got, while living a very short life on a tiny speck on a pinwheel arm of a spiral galaxy, our old Milky Way.
But at the center of the galaxy is a supermassive black hole. So supermassive meaning it's at least 1 billion times the mass of our sun.
Oh my
So
God.
as you think 1 billion suns that is the mass of that black hole, and it's called Sagittarius A star.
Mm-hmm.
So now we named it. That's at the center of our galaxy. And so we've been studying it for a long, long time. Do we know any more than a few numbers? No. We still need theory about it.
Mm-hmm.
But it's a very interesting object to think, over a million billion years, we're going to fall into a black hole.
Is it sucking things in as it goes? Is that why it's a spiral? Is it like a toilet going down?
It depends on how the galaxy evolved.
Okay.
So you have many different types of galaxies, and I don't want to go into the galaxyology here.
Okay.
But you have spiral galaxies, you have elliptical galaxies, you have globular galaxies that are kind of irregular.
Mm-hmm.
And that is just how the stars, planets, rocks, dust kind of accrete around the central object that's pulling them all in due to gravity. Could be a black hole, could be a larger, smaller galaxy at the center.
Okay.
Sometimes it is. Most of the time, it's a black hole because
Okay.
that's the only thing strong enough that can actually pull and hold a galaxy together. And then you have dark matter that's kind of squeezing everything in and holding a lot of things in place.
And for more on specifically dark matter, you can see our scotohylology episode with Dr. Flip Tonato to learn more about how it's everywhere, but we can't see it. We don't know what it does. Maybe you're a ghost. We talk about that.
So, do we know the connection between dark matter and dark energy and black holes? Not yet.
Okay.
Come back and I'll tell you 15 years, 20,
Okay.
50 years, I don't know.
Just a quick question. What is gravity? Where is it coming from?
Good question.
So, if I have flat space-time,
Mm-hmm.
okay, we are talking about curvature now.
Okay.
So now we're talking about space-time curvature. That is the strength of gravity,
Mm-hmm.
right? So gravity in and of itself is the curvature of space-time. It is a force. It's one of the four fundamental forces. Electromagnetism, the strong and weak nuclear force, and then there's gravity. Gravity is always the one that eludes us because we still don't know how it behaves entirely.
Mm-hmm.
But we're going back to this flat sheet. If there's no gravity, space-time is flat.
Right.
As soon as I place anything with mass or energy, space-time curves. And that creates gravity.
So mass is mass, but gravity is space-time bending to that mass. And we'll talk about space-time in a bit. But imagine a wireframe or a grid, and it's stretching and warping around mass and energy. Aha.
Now, how can I curve space-time? Do I just need a static object just sitting there? Yeah, it'll sit there. Or it could spin.
What happens if it spins?
Well, you're creating more gravity
Why is the spinning creating more gravity?
because you're curving space-time.
Oh, because it's spinning, so it's deforming space-time a little bit more.
Not only that, but if I spin faster, I'm gaining more energy. So I'm curving space-time more. So I have more gravity, right? So again, how else can you curve something? Are donuts curved? Yeah, but they have a hole in the center.
Mm-hmm.
So if I have something that's at the very center, right, and it's like a ball or a black hole,
Mm-hmm.
and it's curving space-time, we have gravity. But what if I also have something that's on the edge, but it's more shaped like a donut or a disc with a
Mhm.
hole in the center? We call that an annulus, but
Mhm.
okay.
Donuts, anyone?
Just a side note, when you see an eclipse and there's a glowing ring like a halo from the sun around the silhouette of the moon, that's also called an annulus. And annulus comes from the root word for ring. And an annulus is related to the other hole that sounds like it that you're thinking about.
Disc hole for now. And that has mass energy,
Mm-hmm.
and it's rotating. Does that create gravity? Yeah. Now, if I keep going further and further out, observations tell me, hey, there's this extra mass that's sitting on the edge of galaxies. What the hell is that? Dark matter. Is dark matter creating gravity? Yes.
A lot of it or a little of it or all
Enough
of it?
to keep it creates enough of effect or enough force, right, to keep the galaxy spinning faster than it should at the edge. Now, does dark matter have gravity? Yeah. It only interacts with gravity and nothing else. Is why we can't see it.
Mm-hmm.
Are dark matter and dark energy and black holes made of the same thing? I have no idea.
Oh,
Cliffhanger.
interesting. Oh my gosh. Love a cliffhanger. Okay, so do you think black holes then is one of the theories that black holes predated galaxies because they just started sucking in matter and then that's kind of what made the galaxy gather there. That's kind of what's going
Yeah.
on.
So the term there, and I'm just going to try to keep it super basic,
Okay.
is accreting matter.
Okay.
So we're talking about accreting matter. We're talking about the black hole pulling things in, and at the same time, if you pull something in and you're self-gravitating, you have a likelihood to rotate.
Mhm.
So you're not only pulling things in, but you're also rotating around.
Mhm.
So it kind of creates that spiral look, that spiral geometry. But if you do it over millions and billions of years, then you're going to get more matter, more stars, planets. There are smaller nebula, there are smaller systems inside the disks of galaxies.
And a nebula is this huge blob of dust and gases. And part of your body and your brain might be made up from stars that were made in a nebula. And no, I can't really handle that. But yeah, a black hole accretes and draws in all kinds of things like planets and stars and nebulae and your car keys and my sandwich.
So you could imagine like stellar mass black holes, which are black holes the size of our sun,
Mm-hmm.
in the disk around a supermassive black hole. And there could be 1,000 of them there because
Really?
they're the size of stars. How many stars are in the Milky Way?
Couple of 100 billion.
So you can imagine, well, there's probably some black holes there
Yeah.
falling into another black hole, falling into another black hole that's a much larger black hole.
So a supermassive black hole at the center of our galaxy, but then sprinkled in there a bunch of sun-sized black holes, just dark voids that light and matter can't get out of. And I had a difficult time processing this, and I think I may have dissociated for a moment.
So now it's like, yeah, your face.
Yeah,
Like, what the hell?
What? Can black holes be tiny and in our solar system? Like, is there a possibility that there's little pinpoints of black holes here and there around us, or are black holes only gigantic?
Short answer, and I have to say this, is no.
Okay.
Long answer is yes.
Okay.
But we call them primordial black holes.
What
So
does that mean?
those are black holes that they're not like your traditional black hole, like traditional meaning like the center of the galaxy, like that's our run-of-the-mill black hole.
Mm-hmm.
But these are more these are geared towards much longer timescales. We're talking about cosmology, we're talking about cosmological times, we're talking going back near the Big Bang. What did those black holes look like? And those are on the scales, those are tiny black holes. So we're talking like probably on the masses of like maybe like atoms, molecules, maybe up to the size of like a planet. We're talking about micro black holes.
Mm-hmm.
The mass of a black hole does not matter. The physics of the black hole is the same. Whether you have a supermassive black hole or a micro, tiny, primordial black hole, the black hole physics are the same, as we found out. Theory says that, and theory's been correct so far. There's some holes. I'm working on it. But it's been pretty good so far. Thus far, it's been pretty good.
Pretty good.
There's not a black hole that can just randomly pop up.
Okay.
Guys, don't worry.
Okay.
There's not going to be one in Manhattan. You're going to see it in a movie. It's only in movies.
You're like Dr. Gamble had a bad day. A black hole opens up in a subway. Just like coming to a theater near you.
Right.
Okay, so we're going to talk about the structure of them, but I want to ask you about you. How does one go from a normal person who doesn't know shit about this to someone who is like a theoretical astrophysicist studying the nature of black holes? Like, what?
Yeah.
Yeah, how did it happen?
So you have to be 4 years old.
Okay.
With a solar system placemat in front of you. Pluto was a planet in 1995. And then you ask your mom, does the sun have fire? And that's where my story begins.
Really?
At 4 years old, and she was like, "Oh crap! Okay, I need to put him in something," because she has a degree in biology. She was like, "Okay, I don't do space."
Yeah.
So she did that. So I mean, all along through childhood, through college, high school, whatever, I would just ask myself, "Okay, well, what if? Gravity's weird, but what does gravity actually do? What do black holes do? What's inside of a black hole?" So I looked up okay, well, what are the unanswered questions in physics?
Yeah.
What do we not know yet? Dark matter was like at the top of the list, dark energy. There's another weird thing that I'm probably not going to mention because it's going to take us another hour
What is
segue.
it? What is it?
It's called dark flow, but I'm not going to.
Oh my God, I've
Yeah,
never even heard
it's
of
a
it.
bunch of weird stuff.
It's a controversial hypothesis, apparently, so we're just going to set that aside.
And then, of course, some other things that pertain to black holes and the Big Bang. And I'm like, okay, so, and I looked up, well, why haven't we figured this out? Oh, well, we don't know yet.
Mm-hmm.
I'm like, okay, well, why can't I do this?
Yeah.
So fast forward to college, undergrad, I'm asking my advisor, I'm like, okay, so I want to study black holes. Like, we don't have anybody here that does that. I'm like, okay, well, how do I do this? I'm like, math. And I look up, I open what we call the Gravity Bible, which is Meisner, Thorne, and Wheeler, Gravity.
That's heavy, man.
Thank you, MTW, for all the headache you've given me.
So gravitation, it's a 1,280-page high-level textbook, and yes, it is a religious text to astrophysicists. So it was initially published, first came out in 1973, and the reviews for it still swoon, saying things like, a pedagogic masterpiece. If there were a Rotten Tomatoes for physics books, this would be certified fresh.
And I look, I'm like, oh shit, there's a lot of math here that I didn't know at the time. I'm like, what does this mean? What the hell is a metric tensor and all this? And I'm like, okay, so let me flip. And I go through the glossary, and I'm like, okay, that's a lot of terms. And at the time, I had not taken Calculus 3 yet. So I'm like, okay, let me go back to my actual homework that's due tomorrow, finish this, and then go back on like weekends or my own time and start taking notes. I started just rewriting things I saw in textbooks. I didn't know what they said, I didn't know what they meant, but I knew, okay, I had to practice memorizing some of this so that when I actually went back and I learned the math now, became an expert in the math, I was like, okay, I've seen this before. I've seen it a while now.
So without knowing the full context, Dr. Gamble got familiar with the shapes of the equations, the patterns, so that later the figures were familiar and he could jump into the hows and the whys of that what.
That's the story of how you kind of get interested in it, but you have to be really intimate with the theory, with the actual philosophy of black hole. What's a black hole mean? That's what I asked. And so I was like, okay, well, let me learn everything I can while college is cheap in undergrad. I can just take an extra class because I have a scholarship here and just learn and ask questions. That's what I really did. I asked a lot of questions, both to my professors, to myself, and then others who actually studied black holes. And then I just went and did it. I just found the textbooks, some of the math. I knew I had to learn a lot of math. So I started my graduate thesis, my dissertation, 2 years before I got into grad school.
Oh, wow.
So it was the summer before my junior year in undergrad. That's when I first started learning the math that I knew I would need it for my PhD. So I was kind of like a foresight.
And what was your PhD? What was the dissertation name?
Okay, so here are the words that I can't really ignore.
Okay.
My dissertation was on a nonlinear gravitational wave theory for rotating black holes with a positive cosmological constant.
Okay.
Under a viscoelastic interpretation.
Okay. Once again, that was on gravitational radiation, nonlinear wave theory in viscoelastic lambda spacetime. Yep.
So what that means is I quite literally created an extension to Einstein's theory of relativity that now interpreted spacetime as some elastic property.
Wow. Viscoelastic.
Viscoelastic.
Okay.
So if you think of elastic putty, that's how I envisioned spacetime to act.
Oh my God.
Around a rotating black hole, radiating gravitational waves away. So I'm thinking, okay, this is weird, yes, but I know the math to put this together. And so the math, literally, I was like working with Legos at that point in grad school. I had one.
Literal Legos? Actual Legos?
Sometimes, yes.
Okay.
Because,
oh my God.
Legos are cool, and I had them. If you're a grad student, play with Legos. But the math was like Legos. So we're like building blocks. I could put an integral or derivative together in put tensors together and reconstruct them, break them down, and make new ones. And I made some new math.
Mm-hmm.
It's like fake new math, but it's an operation that didn't exist before, and I needed it to actually do my work. So I was like, okay, well, why doesn't this exist?
Mm-hmm.
Well, if it's not there, then create it.
Yeah.
So again, I was trained as an artist. I put the paintbrush down and picked up a piece of chalk for math. So it's the same. It used the same parts of your brain. That's what I used the whole time. The creative aspect of your brain. That's how I did my work.
And so can you explain where Einstein's calculations don't really apply to some of what's out there? Like, I understand that like dark matter might not totally fit in with the theory of relativity. Like, there's something that it's like, this doesn't work here.
Yeah.
What's going on there?
So no, Einstein's field equations, which is the principal equation for general relativity.
And remember, general relativity is all about how mass affects the 4 dimensions of time and space, but not for all stuff. Things get really weird when you get to particles smaller than atoms.
It doesn't quite work for dark matter or dark energy. We have a best guess. Of course, we have some modified gravity equations. I'm going to leave it there because that's a whole nother topic. But if you go beyond the event horizon of a black hole, right? So that's kind of the outer surface. That's like the point of no return, right?
Yeah.
If you go inside that, relativity fails. We don't know what's going on. So we're kind of taking the equations and we're kind of smearing them closer and closer slowly. But it's not as simple as A plus B equals C. It's A plus a little change in A plus another little change in A plus A. We're trying to sneak up on C or something and not try to use B, right? As a full-fledged equation. But we can only do that but so much. And then they fail right at the event, right at the singularity. We have no idea what's going on. We would need something called quantum gravity.
So gravity theories that work with those subatomic particles. But that's not really happening yet. It's mystery.
But we would need an interpretation of gravity on a quantum scale now.
Okay.
Which, as of right now, we don't have I would say, a consensus for what that theory should look like. We have a whole bunch of competing theories. One of them is loop quantum gravity. We have a bunch of other string theories, another one, but you need at least 7 dimensions to do that. Oh my God. It's madness, I know. But, we're working on, okay, well, very simple questions. Does gravity behave the same way for planets as it does atoms?
And that's where the quantum comes in.
And that's the quantum aspect. Is it the same? If it's not the same, well, then we need new physics.
Oh, boy.
How do we test for new physics? We have no idea. I don't know.
Can you walk me through the anatomy of black hole? Because what I understand is there's the event horizon, which is like where everything's kind of burning up around the edges. And then where is the singularity? And from what I picture it's like a big butterfly net that tapers into something massive. But like, how wrong am I?
I cringe whenever I see that.
Sorry. I just picture the wireframe like
I know,
illustration.
I'm
sorry.
I try not to kill people for it, but it's like, okay, that's the best like mathematical representation we could draw. I'm like, okay, guys, do better. We can. Okay, so it's not a funnel.
Okay, hang on to your hats, people.
So a black hole is actually a sphere.
What?
Yeah, it's actually a sphere. So not only is it a sphere, but because the black hole is rotating, it squishes along the poles. So it's an oblate spheroid.
Wow.
The Earth is an oblate spheroid. It's not a perfect sphere because it rotates.
Like an M&M or like a...
Exactly.
Like a not as squished M&M.
Not as squished, a fat M&M.
Okay.
So if you think of fat M&M, that's what a black hole is.
Oh my God, it looks like a huge M&M.
And that's edge on, right? Okay, so now if we're looking bird's eye view down the pole, you're going to see a perfect circle.
Okay.
Because it has what we call kind of circular or equatorial symmetry. So it's perfectly circular along the equator, but as you kind of go up towards the poles, it changes. It's not a perfect sphere. So now that's the outside of a black hole, right?
So along the middle, perfectly round. Toward the top and bottom, less so. And around the black hole is a corona, and that's apparently 1 billion degrees Celsius, which Americans, that would be 1.8 billion and 32 degrees Fahrenheit, in case you're getting close to one. But yeah, inward from the corona, but before the event horizon, is a hot nightlife spot called ergosphere.
Before we go inside, there's another area right outside the black hole that's called the ergosphere.
Okay.
Ergosphere meaning work sphere, work region.
Uh-huh.
The essence of the ergosphere is that space-time itself, not you, not just the black hole, but space-time itself is being dragged around. So it is quite impossible for you to stay still in the ergosphere.
Because it's getting dragged
Because
around.
it's being dragged around the black hole with the blast. The black hole spin, space-time is being dragged around. So not dragged around like a merry-go-round.
Mm-hmm.
So you can imagine if you were on a merry-go-round, right? And you took a picture, a long exposure picture,
Mm-hmm.
and you went around the merry-go-round, your image would smear, right?
Mm-hmm.
That's what you would see around a black hole in the ergosphere. You could see the back of your own head.
No.
Because the light would be dragged all the way around and hit your eyeballs. Yes.
Okay, space-time in a nutshell. So dragging space-time is so hard to grasp for someone who's like, today is Wednesday, tomorrow's Thursday. Da-da-da-da-da, I'm this year's old. What is space-time in the aspect that it can be dragged?
We're sitting in this studio. I can clock your time. I can figure out your position in 3D, in 4D. But is it actually space-time? No, we are talking about events now, not just points. We have to go to 4D instead of 3D.
Okay.
So X, Y, Z in time. 4D, we're talking about events in space-time now.
So if some cosmic object were flat, it would occupy 2 dimensions on an X and a Y axis. But when something is 3-dimensional, it has that added dimension of depth, and we exist in a 3-dimensional world. So I toss a sock at your face, and that goes through 3 dimensions. But according to Einstein, time is not only money, it's also the 4th dimension. Woo!
So space-time doesn't... Oh, they're going to kill me for this. Space-time doesn't exist without events.
Okay.
Okay?
Got it. Like plotting points, sort of?
Almost like plotting points.
Okay.
Right? So you can imagine the graph itself, like graph paper. If you can imagine you put your dog on graph paper.
Okay.
All right.
And now you can't see the graph paper.
Because you're looking at the dog.
Because you're looking at the dog. But you know that the dog exists at some point on the graph paper.
So we're looking at mass and events, but can't forget that underneath it all, space and time are affected and doing all kinds of mysterious things.
That is space-time. Yeah. It is there, and there may be some quantum interpretation of it that we haven't figured out yet. On a very, very small, we call it the Planck scale. We're talking 10 to the minus 35 meters. Tiny, tiny. Space-time, in essence, turns into what's called a quantum foam.
Yep, it's actually called, I looked this up, quantum foam or space-time foam.
So now in terms of just like a flat or the graph paper analogy, now you're talking about something like whipped cream. So you're talking about like foam on top of a latte in terms of not just events existing, but events popping in and out of existence. What? So now, okay, your dog might be there or it might not be.
Okay, so for more on that superposition too, you can see the quantum ontology episode with Dr. Adam Becker. But back to black holes and what is happening on the inside to affect the outside. So the event horizon is sort of that equatorial mishmash of things going around. Where is singularity?
It's at the very, very center. Now, again, because the black hole is spherical, the event horizon is actually a sphere.
The whole thing is a sphere.
It's a sphere, yes. Now, here's the thing. Here's the caveat. We have 4 different classifications of black holes. You have a non-rotating, non-charged black hole, which is a Schwarzschild black hole. Cool. Mm-hmm. We have a rotating black hole that's uncharged, Kerr black holes. Those are your astrophysical ones, right?
Okay.
we have charged, non-rotating,
Mm-hmm.
and then we have rotating charged.
Okay.
Okay, so that's our little black hole Punnett square.
Okay, so think of charged being caffeinated and rotating being the churning stomach of lactose. So there's an oat milk decaf, non-charged, non-rotating, a whole milk decaf one, rotating but uncharged, a full calf oat milk, charged, non-rotating, and lastly, a rotating charged. Whole milk, full caffeine. And I guess you can get any of those with space-time foam, depending on how good your barista is.
If you have a non-rotating black hole, the singularity is a point.
Okay.
So it's an infinitely small point where all our lines, all our paths in space-time point, and you can't get out. They all
Okay.
point down to the center. As soon as you rotate that thing, it turns from a point into a ring.
Oh.
So an astrophysical black hole, because we assume they're all rotating, right? It would have a ring singularity, not a point. It would be a ring at the very center.
And still tiny, tiny?
And still very tiny, tiny.
What's in the middle of the ring?
We don't know yet. So now you can imagine, instead of you going from a point, you're now going to something that is kind of like a ring, a little surface. So you can think of like a disk that space-time ceases to exist on. And at the very edge of that disk is our event horizon. That's that ring, right? Anything inside that singularity is what we call elsewhere.
Elsewhere? Is that actually the term?
It's the actual technical term.
No way.
It is the actual technical term. We have we have the past, of course, right? So we have the future, okay? Past and future. And if you look at a XYZ plot, if I'm pointing up vertical on the plot, my axis would be like time. The horizontal axis would be space. Cool.
Okay.
A trajectory that's exactly at 45 degrees would be like traveling at the speed of light.
In that tiny of an area, sort of?
In that regard, yes.
Yeah.
So again, we have to think abstractly here. If I am moving faster than light, I'm moving closer and closer towards that spatial axis.
Okay. So the speed of light cuts right through space and time on a graph, which is just a tiny sliver of where it lands. But that angle would change if you're beating light on the speed axis.
Which means time doesn't really pass that much. Which means time is getting slower and slower and slower. But I'm covering more and more space. Elsewhere.
No.
So we have the future that's directly up top. The past that's at the bottom of the axis, right? And then on the sides, left and right, we have what's called elsewhere.
Bonkers.
Bonkers, right?
So time is not viscoelasticity. That is partly like time expanding.
In a sense, yes.
Okay.
But that was a new term that I came up with in grad school.
Okay.
So it's not very popular. It's out there. You can go read my dissertation if you want nightmares.
I imagine there's a lot of math in it.
There's 200 pages of math.
Oh my God. And then if something gets, say, sucked into a black hole, okay, so from what I understand, its gravity condenses in that singularity. Sort of. It's just pulling it into it.
So now you can imagine. So we go back to the putty, right?
Yeah.
So it's the best analogy I can probably give you. Go back to the putty and you hold it in your hand, right? Imagine your hand being space-time.
Okay.
But the putty is like an atom or some kind. If you keep squeezing your hand around the putty, you are simulating space-time shrinking and shrinking and shrinking.
Oh.
Well, what happens to the putty?
Yeah.
The putty has to condense also. But the putty cannot overcome that force, which is gravity, shrinking things down. So now you have no choice but to fall all the way towards the singularity. Well, how long is that going to take?
Yeah.
An infinite amount of time. Because the duration of time becomes slower and slower and slower. But you're covering more and more space.
So putty is matter, and your hand would represent the squish of gravity as space-time condenses. So this matter, the putty, gets slowly condensed toward a tiny point. It's like a cosmic stress ball on a Zoom call that feels like it's never going to end.
Space will stretch out, time will contract.
Nuts.
So when do you reach the singularity?
You could maybe
Never.
never. Oh my
Never.
gosh.
According to our other theorists, you're going to listen to this. According to our theories,
Mhm.
never. But we need new science. We need new physics.
Mhm.
We need quantum gravity. Quantum gravity is probably going to be like the buzzword for this.
Wow.
Yeah,
Okay.
we need quantum gravity.
And there are innumerable black holes out there.
There are probably trillions of black holes out there.
Trillions of black holes. And when
Yeah.
you're studying them, so much of this is theory based on what kind of math can work. What about things like LIGO and things like the imaging of the event horizon that came out a couple of years ago that looked kind of like a glowing orange disk? Okay, so for one of my other jobs, a TV job, Innovation Nation on CBS, I got to interview one of the data scientists imaging this event horizon of the black hole M87, and her name is Dr. Katie Bauman. Let's roll the tape. The event horizon of a black hole is its surface, a sort of point of no return. And therein lies the name of the project of which Katie was a part, the Event Horizon Telescope, an international collaboration capturing images of black holes using a global array of 8 telescopes.
So the glowing orange disk is called a photon ring.
Okay.
You are watching the very extreme matter as it's falling into the black hole. So we are quite literally taking an image of the edge of space-time. If you were to take a picture of the last thing a photon would see before it fell in, that's probably it. We are trying to get even closer. So now I am on a mission concept team to kind of extend that Event Horizon Telescope concept into space so we can look even deeper. So we're trying to appear right on the very edge of the event horizon. What does that look like? What radiation can we collect? What do the photons look like? How are we going to collect weird matter? Do we see anything else there? Is that where aliens exist?
Yeah.
I don't know.
How far away do you have to go to keep looking at those? And how far away was the photon ring that was imaged?
The popular images that you see are both of Sagittarius Star,
Okay.
our Milky Way supermassive black hole, and another supermassive black hole called M87. So, of course, these are catalog names, and astronomers love cataloging things. Yikes. We have very weird names for shit, and I don't understand why. Just pick one system and stick to it. Anyways, M87 presents itself as a very unique and very energetic black hole. It's at the right, perfect angle for observing. It's got a lot of activity around the disk. It's rotating very rapidly, and we like that. It's emitting in all types of spectra across the electromagnetic spectrum, between radio, through gamma rays, cosmic rays, X-rays, infrared, all of them.
This black hole, M87, it's got a nice variety of rays. And we're like, ooh, thank you. We can use these. We like you.
So it's a very nice, well-behaved, as I like to say, black hole. There are others that are out there that are misbehaving. I'm like, why are you doing this? Stop it. Stay still. Stop merging. You don't need to merge again after you've merged a first time.
And yeah, if black holes can't escape each other's gravity, they can swallow each other, like 2 cell phone providers that suddenly merge. And you're like, where do I even pay you bastards?
So that's what we're trying to see. Are photon rings the same around every black hole? Are there other photon rings that we haven't seen? Are there different types of photon rings?
Yeah.
We get photon rings in 2 different directions. What happens? So there's a lot of new science, a lot of new things that are out there. Have we figured them out yet? No. That's why we send stuff to space and observe.
And now you work with NASA.
Yeah.
Yeah. And NASA Goddard, right? And how long have you been with NASA? What was that like?
So I started August 2021. They kind of found me. Of course, everybody applies to NASA, and you send your application out, and you're like, okay, I didn't get picked. I'm going to move on. But then they said, okay, hey, do you want to interview? I'm like, the fuck? Yes. Are you spamming me? And this was the deputy director, my current boss. I'm like, you got to be kidding me. Are you real? Okay.
Did you check the email address to make sure it wasn't like NASA 44455 at Hotmail?
I checked it 4 times.
Yeah.
So I put together like 30 slides of like the work I was doing post grad school. It was unfunded. It was unsupported. I was just doing it on the side. So I was like, okay, one day I'm going to present this to somebody and they're going to like it. turns out it was NASA,
Oh my
which
God.
got me my job now.
Oh my
They
God.
loved it. And I'm like, okay. And you were doing this. Who'd you collaborate with? I'm like, nobody.
Oh my God.
I was like, oh, did you? Okay, so how were you supported? It's like, I didn't have funding for this. I just did it because I liked it. And they were so impressed by it.
That's got to be so gratifying.
It was so gratifying. Now, it gets even better. So I tell my mom this, and she's like, shut up. I'm like, yeah, Mom, with NASA. It's like, when are you starting? Did you get your job? I'm like, they haven't offered me anything yet.
Mm-hmm.
Don't jinx it. It was a 4-month process. Another interview, and that is kind of like when, you know, like my official offer came in and stuff. And I was like, okay, do I leave my current job and work for NASA? Or do I make more money here? Or do I? And my mom's like, why are you thinking about this? What are you doing?
Yeah.
I'm like, okay, yeah, I'm being stupid. Yeah, sure, I'm going to accept. My very first day at my dream job at NASA was the day of my mom's birthday,
Oh man.
August 16th,
Oh, man.
2021. So I gave her my job acceptance to NASA for her birthday. That was her birthday gift. I'm like, Mom, I finally got to NASA. So we both were like on the phone, like, I know, I'm crying too.
Oh wow.
It was truly amazing. And I had to get her t-shirts, and I probably still owe her NASA t-shirts, even though she has 3.
And it all started with is the sun on fire?
It all started with, is the sun on fire? Yeah.
Did you ever find that placemat? What restaurant was it?
I have no idea where it's at now. Mom, if you still have it, keep it, because it's probably gold, because
Yeah.
Pluto is on there.
Yeah.
So, and they
It's
don't make those anymore.
Collector's item either
It's
way.
truly a collector's item.
Can I ask you questions from listeners?
Yes.
Okay, because we have a lot. Oh my God. So many. Okay. So next week we will ask Dr. Ron Gamble, a smart person, all kinds of not smart and very smart questions in the thrilling and the heavy conclusion of black holes, including all of your questions from Patreon. Cryptozoology, lithology, nanotechnology, meteorology, olfactology. We'll be back with the thrilling conclusion of Black Holes Part 2. Stay tuned. Okay.